exam was amazing. Nobody failed it. There were no D's on the exam. There were 9 A's, 2 B's, and 3 C's, which means that everybody passed. Your overall average in the class, there's 8 A's, 2 B's, 2 C's, and 3 D's. The biggest reason why people have D's is they're not turning in labs, are not coming to labs, so you need to do that to improve your grade. There's still time. I will take either lab 1 or 2 late as a makeup lab at the end of the semester, which may help you also. Unless you're dealing with something really big, like internet connections in China, then I may take 2 labs late. I just heard 2 bings, which means that, oh, hold on, let me just see who's here. Is Chris? Yes, Chris, yeah, everybody's here. Okay, so I don't have to call roll again. Okay, so what's going on next is I got a little bit of extra time here, so I'm not so rushed. Maybe I can actually cover this a little bit more thoroughly. Today you had a pre-lecture due. It was in P2. P2 is all about analog circuits, and we use these all over the place. Even inside of a very digital circuit like a memory, there's op amps. There's voltage regulators and voltage references, current mirrors all over the place. These circuits are used even in digital circuits. And if you're an analog designer, you may need to know even more. You've got lab 3 pre-lab due this Friday. You got a very strongly worded message, I think, from the lab TA. I told you guys pick circuit 1. The lab TA sent out an email saying pick circuit 1. There's no solution for circuit 2. Circuit 3 probably has a solution, but it's harder. Circuit 1 is the easy one. Just do that. Trust me, when you see the paragraph of requirements that cannot be met from circuit 2, almost but not quite. I've got an almost solution. Homework 5 isn't due until a week from today. And then we got homework every week. Pseudo spring break. NAU decided to take spring break off the schedule and not tell us, so it's scheduled in your schedule. But we're still supposed to hold classes. What that means in here is that I'm not going to change the schedule. I'm just going to have, it'll be a week that nothing is due, no pre-lectures, no homeworks, and we won't have lab because that's the way it's written on my schedule. No, because the schedule's already written like that. We were about a day short this semester, even with spring break. The last week, our last lab quiz is Thursday, April 15th. The following week, there's no lab, which is reading week. Okay, so I have no reason to add another lab in. You work hard enough in this class that the fact that we have lab days that consist entirely of a quiz is kind of make up for that, because the homeworks are pretty bad in here, and some of that last lab is a doozy too. Okay, you still get your 4 hours of instruction out of here, I think, just by going to class. The movie was fun. It was lighthearted, and there's like 4 people here, and one person on Zoom. But it was great, and it was full of bad puns. And I thank Ben for that choice. We'll do something else later on. Oh. I love this. This is one of my sports. This is where I get competitive. Every year I nominate someone for Outstanding Senior. And they choose like an Outstanding Senior from the EE department, and then they choose an Outstanding Senior basically from the entire college, which is all of kiosk. And only twice in the history of NAU has it ever been a double E. And the standard bearer, the actually chosen standard bearer, not nominated, is Corey Klein.
Oh, yeah.
And those who know of, they just, yes. Yeah, and I nominated him. I nominated the first one too. Jack Gerard. He's now just gets annoying texts from me all the time. He's a grad student in the lab. Classes for fall 2021. You are certainly qualified to take EE380 Embedded Mixed Signal Design. That is my take on everything you need to know as a PUP engineer to get you started in your test engineering jobs. I'm gonna have to add something on test vectors, I realized after the grad students did some stuff. It is heavy on the mixed signal, a little bit of Arduino in that we're using the Arduinos to control analog circuits. Primarily every other semester that it's been taught, except for last semester because of obvious problems, it was half the class was you sitting on the lab bench doing stuff and me showing you, reminding you how to trigger an oscilloscope, how to actually make these measurements that you're going to be expected to do when you first start working, and looking at analog circuits that you don't see elsewhere. A lot of op amps, because they are the workhorse and the glue. Another good course, if you're interested in grad school at NAU in particular, the lab has a lot of funding for grad students. And if you impress Dr. Cambeau, he's got money. Cryptography, a lot of this has to do with you either have to be good at math or programming. I've been through the course. I did not program a single thing. I did encryption algorithms in Excel. They worked. I could get the mathematical concepts behind them. I just did not want to spend time learning to program. That's a good class too. A lot of practical applications. The world is starting to get worried a lot more about cybersecurity and doing things a little bit more advanced than just reacting to what hackers do, maybe actually finding ways to prevent what they do. And his encryption stuff is hardware based. And this is where I come in, is we're using memory devices basically to generate encryption keys, doing low level analog readout on that. So I'm more on the physics and the hardware side of the lab. And there's programmers there too. And there's people in between, and there's math people, and it's more like you would build up a company than you would build up a usual graduate lab. Okay, this happened because of an embarrassing thing when Dr. Cambeau came to talk to my class, and nobody knew about the photoelectric effect, and I just assumed you learned this in physics. When you have silicon atoms, and they get brought together in a lattice, what happens to those chemistry S and P orbitals is they start to congeal into these like energy bands. And inside of silicon crystal, the way it looks is there's an allowed range of states, like S and P orbitals or D, whatever they are, called the valence band. And in silicon, the valence band is almost fully occupied by electrons. Then there's this conduction band. And at 0 degree Kelvin, the conduction band is completely empty. If I put energy into the system, either thermal energy or electrical energy or light energy, I can cause some of the electrons, if I have put enough energy in, to jump from the valence band to the...
Oh, it's cracking. You trying to play?
I'm actually taking this game right now.
Alrighty.
To jump from the valence band to the conduction band. And once it's in the conduction band, It's an electron that's free to move about the crystal. It acts as a conductor. I can have current going through there. Two primary ways electrical engineers use this. The first is LEDs. Now, if I want to get an LED to light up, what I do is I put electrical energy into the system. So I put some kind of electrical voltage or field or something like that. And the electrical energy is enough to excite some of the electrons into the conduction band. They get up here, and the next thing that happens is they start to lose energy, and they're going to have to lose energy in integral amounts of that band gap energy, because they can't end up in the middle of the state. They have to go all the way from here back down to here. Since the frequency of the light, this is Planck's equation, is proportional to the energy of the gap times Planck's constant, h, and its cousin h bar, not that it's not in that equation, I get a single frequency of light based upon what the band gap of the device is. For silicon, the band gap turns out to be in the near infrared, which is why we don't have silicon LEDs. Most of them are made from aluminum gallium arsenide, aluminum gallium phosphide, aluminum gallium arsenide phosphide with different concentrations of the last two things, and things like that that give you a small enough band gap that the light comes out invisible. It was a really big deal. Blu-ray, why it's called Blu-ray, is they used a higher frequency laser that was in the blue light. They had to develop a material that actually had a band gap in the blue light region in order to do that. It took them a long time. There's another thing that can happen here too. What if I have photons hitting this thing? If photons hit it, they're putting energy in. So now I have light energy coming in, exciting the electrons from the valence band into the conduction band, and electrical current flows. You've got a photocell now with bad efficiency, and then there's the whole engineering thing is to try to develop and get that efficiency number up. So this is Planck's constant, and this is basic physics. I'm sorry, right? Yeah, I just assume you learned that in physics. I'll have to go teach physics in order to rectify that situation. This is the Finley. Does anybody remember Michael Finley? Okay, yeah. This is the guy who did the banana eating contest. He went off and got a master's degree in audio engineering, and he was actually had a band too. The Curly Tops. They would play, but he was a big into audio as in musical, and he has actually ended up at Micron now. When people build amplifiers for audio, they talk about classes a lot. I'm going to start and probably go through the first 4 or 5 slides in here just by doing this. Let's get some background on here first. This is the voltage transfer curve like we plotted in lab 1 and you saw on your exam and everything for an inverter. Remember, for an inverter, there are 2 places in here where the magnitude of the slope was -1. We'll say about here, maybe about here-ish, and I'll move those as necessary later. And when I'm here in this region, the transistor, the NMOS transistor would be in triode. No, it would be in cutoff, sorry. It doesn't really matter that much. It would be in cutoff, and down here, for this argument, it doesn't matter. And down here, it's in triode. In cutoff, we use one of them as a digital on state and one of them as a digital off state. We have 3 regions of operation. The other one's saturation, so that region where it's slopey in the middle must be the saturation region. The good part about this is we can use the transistors in the saturation region. In the saturation region, they have gain, and there's a good picture, so I don't want to talk about too much about this right now, but I can use the transistor for gain. In between those two M equals -1 points, it's no longer acting as just on or off. It has slope. If I put a small signal on VGS, I get a big signal on VDS. Now, the whole amplifier class thing that we don't talk about much in here, other than the best linearity or best current draw, 2 things. Best linearity is class A. Linearity. If you think about it, if I'm amplifying about this point Q, that's right dang smack in the middle of the saturation region, if my signal goes up above it, it's still got a pretty constant slope. And if it goes way below it, it still has a fairly constant slope. And of course, there's a drawback to this. This also has the highest current draw, so it dissipates the most power. When we want to amplify things for best linearity, we put the operating point. We can choose where our VDS and our VGS is for this transistor. We're going to pick it so it's right in the middle. Now, if I want to draw the least current out of this circuit, let's just go all the way to the extreme. If I draw 0 current out of this circuit, what would VDS be? Ohm's law. I equals 0. What's the voltage drop across a resistor with no current? 0, right. So my output is just sitting here at VDD. This has no current. VDS is high, I is low. If VDS is low, I is high. Okay, so the place on this curve where I get the lowest current, where it's still linear, is right here. But you can see right here, if I put my operating point right here, where that dot is that I'm drawing right now, I'm going to have, if I try to amplify a signal that pushes it this way, I turn my transistor off. That is the whole idea behind class B. So this is A, and this is B. Is I make it so the signal is what turns the transistor on. I don't put bias current through it to turn the transistor on. I let the signal turn it on. Highly nonlinear. There's a whole nother talk about this in 490 the fall, but I get the least current draw. We're going to use this in places where, like, I have a battery operated system. I've got a cell phone and I want an audio amplifier in there. I'm going to push it more towards class B to get that power draw off the battery down. But I'm going to lose some signal integrity. I'm going to lose some linearity. True class B, I actually operate right here, and it takes signal voltage on the gate to turn the transistor on. So I don't have voltage draw. I don't have signal unless my signal is above V threshold. And during the negative parts of the signal, I have no signal at all. Surprisingly, it's not as bad as it sounds. It doesn't sound as bad as you think it would, losing half the signal. But class AB is a hybrid of this. I just add a PMOS signal as transistors that amplifies in the negative half of the cycle. So in that case, I'm only losing signal between plus and minus V threshold. And that's not so bad. And the signal is what provides the bias to turn it on. Much lower power consumption. And then we get into class F, which is where I only amplify, like, if you think of the whole signal as being 360 degrees, I may only be amplifying 40 degrees out of that. And you can reconstruct the audio signal using DSP magic, which I don't do. I gotta have something I don't do, right? So this is where I get to combine my EE188 skills with transistors. The thing that I see on exam 2 in here where people mess up the most is the basic 188 stuff. Do that when you're doing the homework. Look at the circuit. Label everything you know. Go through, apply KCL, apply KVL. Think about if there's a resistor and I know the current through it, I know the voltage drop across it. If I know 2 of the voltages, apply Ohm's law in many, many ways. And remember Ohm's law, you always say V equals IR. And I think that messes you up more than anything else. It's not V equals IR. V is a voltage difference. So it is actually the voltage at the positive terminal minus the voltage at the negative terminal equals IR. So you need to know the voltage on both sides of the resistor to get, or you need to know the voltage at one side and the current in the resistance to get there. So now I get to be Dr. Evil. This isn't nearly as bad as after exam 2 when we start doing Bode plots. I just had to say that word. 280, we're doing Bode plots now. So let's talk about some small signal operation. Today, the goal is to get through some of the DC biasing circuits. This is the 188 stuff. This is the stuff that people who make in the teens on the exam screw up and they can't do anything else. Okay. This will get you about 50% on the exam if you can do the 188 stuff. After that, we'll talk about MOS amplifiers with a resistor load. We'll talk about some small signal operation, and the small signal model you've already seen in 280. That's the one with RO and the little dependent source in there. We're going to talk about the basic MOS amplifier configurations, common source, common gate, common drain, common source with source resistor, which is different. And we'll talk about biasing. Then we'll move into diff amps and cascodes and more integrated circuit type analog. I get a half a class to do all of analog. This is when I started writing senior electives. So here's the basic idea. We have the voltage transfer curve just like we did for a digital device. What I'm doing here is I have a VGS axis. This is my input. I have my VDS is my output. This is a common source amplifier. So this is V out. And I have a transfer curve that looks like this. If I provide bias by putting a VDD and an RD in, I put enough current to set the DC operating point. The DC power is going to provide big V, big D, big S, and big V, big G, big S. That's the DC part of the signal. I put a little v, little g, little s. I put an AC part of the signal in there also. So I've got 2 inputs, both a AC and a DC. The little v, little g, little s is varying with time. If I'm at this point on the curve, my output from my curve, I would expect to be up here. And if I'm at this part of the signal, I'm expecting my output to be down here. My output is much bigger than my input. I have amplification. I can power my big booming speakers. Right. All right, we did this. We use the saturation region. That's a good point for this slide. Because in the saturation region, I have a big slope on this line. And look, it's the slope that gives us the big difference on the output. So I need that slope in order to amplify. Okay. Since we are in linear world here, in order to make these devices act in analog mode, your first assumption is that the transistor's in saturation. This is going to help you solve for other pieces of the circuit. At the end, a lot of times I ask you to go back and verify that the circuit's in saturation, because really common mistakes are that I've got this circuit and I think it should work, and it's not amplifying what's going on. It's not in saturation. So it's always a good mental check. And in the lab, when we're doing this at my other school, we're doing more linear stuff. First thing I would do was put a voltage probe down at the gate, source, and drain of the transistor and verify it was in saturation. And generally there's a problem there, and I could pick out which terminal wasn't working. Go back to oh good, somebody's yelling at me. Analog occurs with both AC and DC. You need a DC bias point, and you could be, you're amplifying, it's probably, what you're amplifying is probably not AC if you're thinking like a pure sinusoid. It can be. But usually you're amplifying something like a voice signal, which is a whole combination of a whole bunch of different sinusoids. And, or you're looking at a modulated signal coming out of a transmitter. It could be FM modulated for radio. Again, it's going to be a combination of a bunch of frequencies. So it's AC plus DC that makes these things work.
But you couldn't have it with just DC current alone, right?
Yes. You can amplify DC in a weird little way, is what we did in 188, which I didn't like. It's called level shifting, basically. But mostly we're looking at things that have some AC component on the input.
All right, thanks.
Okay, since it's in saturation and you assume it's in saturation, we're going to use the saturation. Oh, please tell me. Okay. Well, I'm in between. I know I have a cow every time my pen doesn't work. It usually means my computer's frozen. Okay, or I'm in between slides. In this case, I was in between slides. Since it's in saturation, we can use the saturation current equation. We're not taking into account the body effect, and we're not taking into account the output resistance, the 1 plus lambda VDS, because this is like a first order approximation. And what we're going to end up doing is putting that effect of 1 plus lambda VDS into our basic circuit model of the transistor with that little component called RO. That's not a real resistor. Remember, VGS over VT is commonly called V over voltage. My shorthand version of this equation, because I write it so much in here at this point, Kn, sometimes I forget the 2 squared. Kn prime is just Kn. Wait, Kn is Kn prime W over L. VOV is VGS minus VT. If I know VGS, the rest of the parameters in that equation are fixed for that transistor. I can calculate ID. So if I know IGS, I can get ID. I know VGS. I can immediately get ID. That is circuit analysis trick number 2. If I know VG, well, if I know ID, I can plug it into this equation. All I did is I took this equation right here and solved it for VOB. Did a little bit of algebra. If I know ID, I can immediately find the VGS value. And we'll go through this amazingly methodically today and much slower than I normally do because of pseudo spring break. Maybe this is why this class has all A's. I'm just going to accept it. The new dean, the old philosophy for a while there was we had to fail as many people as we possibly could. When I first got here, it was pass everybody. This isn't your 80s engineering school. And then it got to be just fail everybody. And now they're swinging back the other way. It's just like, we need to get our DWF rates down. So just pass everybody. What do I care? And then I'll swing back. Oh, we're passing too many people. We're going to look at some examples from the book. This is from the Cedra Smith book. A couple of really basic circuits. This is the part that a lot of people mess up that fail exam 2, is this basic DC biasing. So I wanted to spend a little bit extra time here. I officially have 4 days. I'll probably take 5. And use up one of the students from the break days. Dr. Brower doesn't like this. That's why it's a big red X over it. I don't particularly care how you do it. I don't care how you label it. I want you to label it. Label your currents. Remember for, I was going to erase that today. Remember the current through the drain on a MOSFET transistor also equals the current through the source. If you know the current on one side of the transistor, you know the other. Label your power supply voltages. Label your positive and negative terminals. And you missed one there, Dr. Brower. This would be positive and this would be negative. On your voltages. If you come up with the same answer as me, but it has a different sign, the first thing I do on the exam is I go and check to see how your circuit is labeled. If it's labeled upside down from what I thought it should have been, and your answer is negative, it's a perfectly right answer. If it's not labeled, it's a sign error by default, because I don't know what the heck you meant. So label your schematics. In Mentor Graphics, if you want to find the current through a device, you click on the device. Currents go through devices in Mentor Graphics. Voltages are, you get voltages by clicking on the node, currents by clicking on the device. Put your plus and minus signs and your current arrows on your schematic. Otherwise, you're going to make sign errors all over the place, and I'm just going to consider it to be a sign error anyways. So here we have one transistor. We're given some information out of the transistor. My diagram is already very nicely labeled. If I draw them, they may not have all the labels on them. I'm given VTN is 4/10 of a volt. I'm given Kn prime. I'm given this W over L. Okay, 150 lambda over 5 lambda. Give me a break on this. Don't put this in, don't put 150 lambda over 5 lambda in your equations. You can reduce that fraction, and this equals 30. Do that. It will save you a whole bunch of algebra errors. Okay. Now we're given a design goal. ID's 50 microamps. So I'm immediately going to put that on the schematic. It helps me solve the problem. Writing it down. 50 microamps. That's ID. That is also IS. So I know a lot more about this circuit now. Now we got to do some thinking. This is the Class A thing. What is the maximum VD I can have? The maximum voltage at the drain. Well, if I do the thought experiment, if I actually have this where the AC current, there's no AC current in here, but if I drop the current down in the circuit to 0 microamps instead of 50, I'd have no current flowing through RD. And so the highest voltage I could get out of there, my voltage drop would be 0, would be VDD, would be 0.9 volts. Okay, everybody okay with that? You're only going to have to do that 100 times between now and the next exam. The minimum value of VD, okay. The absolute minimum value of VD is going to be this negative power supply voltage, but I'm not going to use that because I have another limit on that. The other limit is I have to keep the transistor in saturation. So to keep it, oh, that's just beautiful. To keep it in saturation, I need VDS greater than or equal to VGS minus VT. And I'm ignoring the body effect. So I could say, I'll do this once. VDS is VD minus VS. Otherwise, I get a bunch of questions about this. VGS is VG minus VS minus VTN. Now I add VS to both sides of the equation. So what I actually need is I need VD greater than or equal to VG minus VTN. Okay, what do I know? The gate is grounded, so VG equals 0. I got that from the diagram. So my VD has to be greater than or equal to 0 minus 0.4, negative 0.4 volts. And thank goodness that's more than my power supply voltage, so I'm okay. This is my real limit. And that's to keep it into saturation, minus 0.4. Now, in order to get the best linearity, to get that Class A amplifier amplification, I want to put my actual VD that I'm controlling with my DC input to right in smack dab in the middle. Those of you who remember algebra in high school can use the midpoint formula. For those who only taught algebra in high school and can't remember the midpoint formula, this is what I do. I take the max value, 0.9, and I subtract off the min value, minus 0.4, sign error waiting to happen there. I divide it by 2, and that gives me how much higher than the midpoint, than the bottom level the midpoint would be. And then I add that to the minimum value. That's my version of the midpoint formula. And that comes out to be, whatchamacallit, I've got, thank goodness I got my notebook in front of me, is positive 0.25 volts. Minus a negative is positive. So VD in the middle is 0.25 volts. I've chosen my operating point to get my transistor with the best linearity. I'm going to write that down on my schematic. My VD is 0.2 volts. Now this is where Ohm's law comes along. I don't know how many people have been screwed up in electronics and in Auburn and in my whole world, just because they think V equals IR, they pick one of these voltages and say V equals IR. It's a voltage difference. So the voltage difference across RD is VDD minus VD, and its current is its current, and its resistance is its resistance. we can plug in a whole bunch of numbers here. 0.9 minus 0.25 equals 50 micro times R. So that's how we solve for R. And you'll often, I don't know if it'll happen this semester, but sometimes I just go VDD minus IDRD. VD is VDD minus IDRD, and all that equation is another rewording of Ohm's law. If I teach you that equation, you mess up things on so many levels. If I teach you Ohm's law and it sticks, you'll have a skill for life. Okay. We solved that equation for R. One equation, one unknown. What do we come up with? 13 kilo ohms. 13 kilo ohms. Okay, I write that down because I know something else. Now we want to find VGS. So this is another one. Okay, we've figured out all the rest of this stuff. I've got VG. I don't know what VS is. It's not negative 0.9 volts. I can tell you that much. I've got another resistor here, RS. Oh, no, I can't, and then never mind. I just stopped what I was gonna say. What? Yeah, they are. All those weird little marks are showing up all over the place. The letters and the numbers. Let's erase this for a minute. Oh, that helps. Let's erase some of this so I have some more room. Okay. Now, remember I told you that we were in saturation mode. I know ID. I know V over voltage. Okay. So where's the, okay, so V over voltage is going to equal the square root of 2 ID over Kn. 250 micro, Kn is Kn prime W over L, so 200 micro, and we decided W over L was just plain old 30. And I plug that into my equation. For NMOS, you take the positive square root. For PMOS, you take the negative square root. We'll get by, I have a whole slide on that. It's 0.129 volts. Okay, VOV is just VGS minus VT. VT. I know VT, it's 0.4, so I can get VGS is 0.4 volts. Bigger than that, VGS is 0.529 volts. Yay, I got another thingy. The hard part on the homework is a lot of times you don't get the steps in order. You have to figure out what to do. Write everything on the diagram, Ohm's law, and this silly equation. Okay, if we know VGS, this is an application of KVL. I'd like to get you past that though. This is the plus side, this is the minus side of VGS. I have 0.529 volts across there. If I take 0 volts and I drop 0.529 volts across that, the only way I can have positive 5.29 is to make this negative 0.529 volts. So we know VGS, and you can do this algebraically too, if you really want to torture yourself. VGS is 0.529, which equals VG minus VS. VG is 0. Solve for VS. It can be done. Or you use my circuit trick, or you use KVL, and everybody hates KVL. So we've got VS. It's negative 0.529. If it comes out greater or more negative than this number, I'm in trouble. If I get an answer that's more positive than this number, I'm in trouble. I've either made a mistake or something's really weird. Okay, now we want to find RS. We're going back to Ohm's law. If you do it this way and to stop trying to remember stupid formulas, this works. So across RS, I have V plus of RS minus V minus, the voltage at the negative terminal of RS, has to equal its current times the resistance. We want to solve this for the resistance. I've gotten VS. And be careful here because it's like sign errors. Every time I put a negative power supply in a problem, I can just watch the sign errors multiply. The positive terminal's at negative 5.29 minus the negative terminal, which is minus 0.9. So I actually have a positive voltage across it, even though both voltages are negative, equals 50 micro times R. And I can solve for R, and I can guarantee you, if you ever solve for R and it comes out to be a negative value, you've made a mistake. I've had people insist that they were right, and that's usually when I miss Sharper. That was usually when I would send them down to Sharper and say, I really, you really got to go ask Dr. Sharper, he's not a doctor, but you really need to go ask Sharper for a negative resistor. The thing is, Sharper would sit down and patiently build an op-amp circuit with them that would model a negative resistance. But it was good learning, especially for people who thought resistors were negative. R, I miss Sharper. That was a shame. I'm still upset over that. RS comes up to be 7.42 kilo ohms. Again, we haven't done anything fancy. This isn't hard like the resistor network, finding the REQ in 188 where the whole resistor network looks like a pentagram and you're standing in the middle of it trying to find the REQ. But it's applying those basic principles to a circuit that just happens to have a transistor in it. Okay, we got our S. 7. Oh, wait, that got weird. 7.42 kilo ohms. PDC. A lot of people graduate from college and don't know how to find the power dissipation across a transistor. I don't understand either. Okay. At least good. I got one look of how could that happen. The power dissipation in a transistor is the current going through it, P equals IV. The current going through the transistor is ID for a MOSFET. And its voltage drop, the voltage that we're going to use, is the voltage that's dropped between the drain and the source, because that's where we're going to generate heat. So it's ID VDS. I don't understand either. I see the mistakes on the exams though. ID is 50 micro. VDS is VD minus VS. So that is 0.25 minus negative 0.529. And if you think about that, if I have a positive voltage on one side and a negative voltage on the other side, I better have a bigger magnitude. They're not going to subtract. And we can calculate that, and it's 12.5 microwatts. This is a really important number to calculate before you power up your device. Transistors, if you buy discrete transistors, they come in packages. And the different packages are rated for different power dissipations. If you're running a power circuit that's driving a motor, you may have a 0.5 watt dissipation across that transistor. You get one of those little bitty tiny transistors, you're going to blow it. It will burn out. Even if you get a 0.5 watt package and you are really pushing that 0.5 watt limit, like somebody did on a capstone project. You're going to generate enough heat that you're going to blow your transistors. If you get the big packages, there's this big metal chunk on the back of it with a screw hole on it that has a purpose. That is so, what?
Sorry, I just had a question about how it's 12.5 microwatts.
Oh, it is, I think that's right.
Because if you subtract 0.5 to 9, obviously it'll be 0.779.
You're right, I did that calculation wrong.
It's like 38.9.
Okay, you're right. And I'm looking at my notes and I did that calculation wrong. It's 38.9.
Yeah.
Okay. Okay. So the big metal tab on the back of the transistor, that's 38.9 microwatts, is so that you can screw the device down to a heat sink. And that will help you dissipate a little bit more power on the device without damaging it. You can get the heat out of the package. You can run it at a higher temperature. You can run it at a higher current.
How do you can like audio stuff? Why would you need to run a huge transistor like that in audio?
You're trying to, okay, audio amplifiers, big booming speakers. You're trying to turn the wheels on you're trying to turn an electric drive, the wheels on a motor, where you're running a lot of DC current through them, or a lot of AC current through them, depending on what type of motor you have. Anything that produces effects in the outside world. A robotic arm. You're going to be using a lot of power to move a heavy robotic arm.
You can't just pulse width?
Well, you do that too, and that helps. The pulse width modulation helps. It increases the efficiency. But at some point, when you're kind of like pushing the limit, you have to heat sink. And even tiny electronics need heat sinks, like graphics processors and things like that. So. And sometimes people forget to do that. Okay, this is a diode. Yay. There's a point to this. It's our next circuit. If I put positive voltage on the positive end of a diode, current flows. I get forward current, and it's going to be whatever current I need to meet the requirements of the rest of the circuit. If I put positive voltage on the negative terminal of the diode, I get nearly zero current. It will be a small leakage current. We'll have to use the leakage current later, so we'll call it nearly zero. Nanoamps, picoamps, something like that. You can, since diodes are harder to build in a CMOS process than transistors, a lot of times if you want a diode, you use this trick called a diode connected transistor. And this is what it looks like. Now there's a right way to do this and there's a wrong way to do this. Let's look at the wrong way to do this first, and that's part B. This is the drain, this is the source, and this is the gate. I'm calling that the drain because it's going to the more positive voltage. What is VGS on transistor B? Zero. They're connected together. VGS equals 0. If VGS equals 0, it's always going to be less than the threshold voltage. ID equals 0, or the leakage currents. That is the wrong way to do it. You do not tie the gate and the source together to get a diode connected transistor. You tie the drain and the gate together. So drain, gate, and source. Now in this case, VD is usually going to like a power supply, maybe VDD. I get a big voltage on here. So now I have a big voltage on the drain, which also is tied directly to the gate. So I have a big voltage on the gate. The source voltage is lower. I have this transistor's turned on all the time. and it's acting like a diode. It drops a small amount of voltage and supplies current to the rest of whatever it needs to drive. Usually I see these used as pull up and pull down transistors is what I call these diode connected transistors in larger circuits. Boy, you should. I had a normal semester. A lot of the times I'm just going through here. This is the equation. You can plug in the numbers and figure it out. Next slide. It's like, okay. So we've got, and this would be a great place to do that, and I'm really tempted to do that right here. We've got this transistor, diode connected. I want the ID to be 100 microamps. It's in saturation. I want to figure out what VGS is. So I write down the equation and then plug the numbers in. VOV equals 2ID over Kn prime, I'll write the whole thing, W over L. And VOV is the same thing as VGS minus VT. So we've got VT, we've got ID, we've got Kn prime, we've got W over L equals 30. We can plug that into the equation and solve for VGS. So if you want 100 microamps, you're going to force VGS to be, I'm not going to plug in the numbers. I can't even do that this semester. We're going to get the number to be 0.583 volts. Is that VGS? Yes. Okay. If you really need to see that calculation, it's in the slide solutions. Maybe I want VGS to be fixed. I want VGS to be 0.65 volts. I plug in ID, Kn over 2, VGS minus VT squared. And I know everything in that equation. Kn is Kn prime W over L. Or I have to write that down at least once. Watch the primes in this unit. There's CL and CL prime and RO and RO prime and RD and RD prime, and they're all different. The little tick mark matters. Okay. We can, if we know VGS, we can find ID. And that's just plugging into an equation, and hopefully you know how to do that. 188 microamps. So I can either use the current to set the voltage, or I can use the voltage to set the current. Okay. This saturation region equation, I promised you this slide was coming. For NMOS, this works, and this is what we've been using so far. The only difference with PMOS, it comes out, if I want to find VGS, I have to take the negative square root. Use the positive square root for NMOS. PMOS is wrong, so use the negative square root. Okay. For most of these calculations, we've been ignoring the channel length modulation. This is the 1 plus lambda VDS. I'll stick it back in my small signal model. I'm just trying to find the DC operating point. And you want to get this really accurately, use a simulator. Kn and VTN are known. We ignore the body effect. Again, this is hand calculations, and we don't want to drive ourselves crazy. So we just assume the threshold voltage is a constant. The two variables are always ID and VGS. If you know one, you can calculate the other. I'm going to claim there's a third variable in this equation. What if you know the ID you want and you know the VGS you want? You can tune the W over L ratio of the transistor to make this equation work. We have W, oh great. We have W over L embedded in there. Kn prime W over L. You'll get to do that on the homework occasionally. You'll think you know too much. You know ID and VGS, but you don't know the W over L. That's usually what you have control over as a circuit designer, is W, not L. And this is more calculations of the same. I know VGS, what's ID? I know ID, what's VGS? If it's PMOS, I just have to remember to take the negative square root and the same types of things. And the details of that are in the slide solutions. And I don't want to bore you to tears. There's a lot more to cover. A lot more. And then there's a cat picture. Yes. This is hard. It's hard the first time anybody sees it. It was harder for me because I had one of the evil Bagensky brothers teaching me this. Which one taught me this? It was the one that looked like Paul Simon. They weren't actually brothers. They were first cousins. One looked like Paul Simon and one looked like Robert Plant. But they were both equally evil. And he just hated students. He was a PhD student. But the way you get to where it's practice, and some of this is time spent on the homework, trying to do this. You will have questions about the homework. You'll tell me that people will come in and tell me you didn't tell me this. And I can say, oh, look at the TSMC file or something like that. I do not mind answering your questions. I'd rather answer your questions at any time I'm in my office by email or whatever it takes, than have you stuck on the problems. I want to see you guys succeed. And just don't try to do the homework the night before, because I don't answer questions in the middle of the night. It's walking on a tightrope. Or it's like a fence post. Tiny little kitten. Probably the first time she fell down a few times, but she's a cat. She'll figure it out. You guys will fall down a little bit too. Practice. Practice doing your circuits. We talked about this. I don't want to do this again. Well, this slide will come up again tomorrow. We have a voltage reference voltage circuit. What I want to get out of this circuit is I want to have VD equals 0.7 volts. That's my goal. So for this DC analysis, I'm going to set it to 7 volts. I know the things about my transistor. This is 50 lambda over 5 lambda is 10. Yeah, and we got lambda from the TSMC data sheet, was 0.09 microns. You could do that or just say the transistor's 10. We have to figure out what's going on here. Okay. We've got VD, and if we look at the circuit, VD's tied to VG, so VG better be 0.7 volts. My VGS is between 0.7 and ground, so my VGS is 0.72. Diode connected transistor again, 0.7 volts. Since we know VGS, we know ID. ID, Kn over 2 VOV squared. Kn's 200 micro over 2. W over L was 10. And VOV is VGS, which we figured out was 0.7, minus VT, 0.4, and then square it. So we get ID. And this is number 7. Someone just barked at me. It is 90 microamps. The answers for these mostly should come out in microamps, maybe milliamps. These are circuits on a board. Okay, we got this one. Check. There's some places where I just give you a big Excel table and I ask you what all the values are, and you have to figure out what order to do them in. You have trouble starting, ask me. That's what I'm here for. RD, okay, I have a resistor. I know the voltage on the positive side. I know the voltage on the negative side. I know the current, I just got that, 90 microamps. I can use Ohm's law and solve for RD, the magic resistor that will make all this happen. So V equals IR, which means I equals V over R. So R equals the voltage difference, 1.8 minus 0.7 over the current, 90 microamps. And we can get R. It's 12.2 k ohms. So I write that down. V over voltage is just VGS minus VT. I could have done that right off the bat. VGS minus VT, because we know VGS is 0.7 minus 0.4 gives you positive 0.3 volts. Okay. Ways I can screw you up on the exam: put a negative power supply in. It confuses everybody, and make you apply Ohm's law. This is called a current mirror. Probably one of the most common circuits you see inside an integrated circuit. I want to set the current bias for any analog thing. This is like magic. I could do this over and over again. We use this on the crossbar chip several times. Okay, what am I given here? I'm given VD1 equals VD2. They're both 0.7 volts. This is 0.7 volts. I'm given VDD, 1.8 volts. So I plug that in every place I see a little arrow. M1 and M2 are matched, which means they were designed on the same processing line on the same day. So they're almost like identical twins. There's small defect differences, but not a lot. W over L is 10. And we want to figure out what's going on here. Maybe I'll just finish this circuit and call it a day. For transistor 1, it's diode connected. So VGS1 is going to equal VDS1. It's 0.7 volts. We can plug that into the equation and solve for, we know VGS, we know ID. I'm just going to give you the number here. We've done this a couple of times today. ID is 90 microamps. It's just the same numbers we used in the last one. 90 microamps, I use Ohm's law. This was the saturation equation. I'm going to use Ohm's law to get this one. I've got 1.8 minus 0.7 over 90 micro gives me R1, which is 12.2 k ohms. We'll get to the magic in a minute. Okay, now I'm looking at this, and since the gate of M1 is tied to the gate of M2, they must have the same voltage. Oh, no. Not that one. That one. The gate of M1 is tied to the gate of M2. We must have the same voltage. If they have the same VGS and then they have the same source voltage, both tied to ground, so VGS1 must equal VGS2. And since they're perfectly matched transistors, they have the same VGS, they have the same ID because of this equation right here. 90 micro. What happened to all my stuff? Oh, I didn't have much. So this is also 90 micro. I'm going to set R2 to be the same thing to get this same circuit, 12.2. What I have built here, I have built a circuit, and this is why we use it a lot. I can supply a current from an external source into this circuit. And I can build hundreds of these things attached to the same gate and match the current perfectly. A lot of times we don't care if our current source is 100 nanoamps or 105 nanoamps. What we care is that every circuit in there has the same current. So we use this to match current across a device.
So in this case, when we set up our meter, we only tie one drain to the gates, and then if we tie the other one, we just short circuit through.
If you tied the other, yeah, that would just be weird. You only need to tie one of them down to get this. Every other one looks like this version of it. So I can copy that over and over again and supply the same bias current to every ReRAM on the row. And set that with a lousy DAC and not care about the exact set this value with a lousy current output DAC. Don't care about the precision on that as long as I perfectly match the currents in each one of the columns. And we'll have a better way to build that later when we get to part 2. How much more did I, oh yeah, we don't want to talk about that yet. This is an op-amp. It doesn't look like an op-amp. And it'll never look like an op-amp until I draw the triangle around it. Oh, we're almost done. Okay, we are done. It's time. Okay, keep up with the homework. It will really help you. Exam 2 is harder than exam 1 because we're no longer dealing with the digital world. We're dealing with the analog world. Get some practice with that circuit analysis. Do the DC bias circuits. Make sure you understand them. Make sure you understand the homework more so than you just get the right answer. Getting the points isn't worth as much as the understanding. Some of these circuits that we've seen today look familiar from my exams. So it's basically just kind of going through the same thing. You know, get the easy problem, get the easy parts, and then the rest falls into place. Okay. We'll see you guys on Thursday. Maybe soon.
What?
I said some of you maybe soon. Oh God, I can't skip. The good thing, okay, I'm not recording. I'm gonna stop recording. Everybody's here. I'm gonna stop recording before I say this.